Hello and welcome to this deep dive into the fundamental building blocks of modern artificial intelligence. Today, we embark on a journey titled, From a Single Spark to a Thinking Architecture. Neural networks, the engines behind today's most powerful AI, often seem like black boxes of impenetrable complexity. But the truth is, they are built from remarkably simple, understandable components organized in sophisticated ways. Our goal today is to demystify these foundational elements. We're going to trace the evolutionary path of the artificial neuron, the single spark from which all deep learning originates. We will learn how these tiny computational units work, how their limitations were overcome, and how they are organized into the powerful, multi-layered structures that we call thinking architectures. Understanding these core concepts, the neuron, weights, bias, and especially nonlinearity, is absolutely essential. If you grasp these building blocks, the rest of deep learning, including training methods and advanced models like transformers, becomes significantly more accessible. Let's start at the very beginning by comparing our artificial models to their biological inspiration. When we talk about neural networks, the immediate reference is the human brain. However, it's crucial to understand that our artificial models are vast, strategic simplifications. As the slide suggests, real neurons are complex biological entities, intricate cells using a delicate mix of chemistry, physics, and electrical impulses to communicate. They have specialized structures like dendrites to receive signals and an axon to transmit output. Our artificial neurons, often simply called units, are a sheer mathematical abstraction of this process. They capture only the essence of the operation. If you look at the diagram of the unit, it takes multiple inputs, each scaled by a weight. This weighted input is summed up the sigma symbol, \sigma dollar, and then a function, $, is applied to determine the output. While this abstraction allows us to model complex behaviors computationally, it sacrifices almost all the biological fidelity. We don't try to replicate the precise chemical dynamics. Instead, we focus on the core information processing task, translating multiple weighted inputs into a single, functional output. This extreme simplification is precisely what makes neural networks computationally efficient and scalable across massive datasets. The history of the artificial neuron starts long before the current AI boom, specifically in 1957 with Frank Rosenblatt's invention of the perceptron. The perceptron holds the historical distinction of being the first mathematical model of a neuron capable of learning. Let's break down its simple, 5-step workflow, which forms the basis for all neurons that followed. Step 1. Inputs, which are the raw data points. Step 2. Weights W1, W2, etc. These adjustable parameters determine the importance of each input. Step 3. Summation \sigma dollar. This is where the magic happens. All inputs multiplied by their corresponding weights are added together. The results so far give us a total weighted input. Step 4. The threshold test. This is the perceptron's simple activation mechanism. If the summed result is greater than a specific threshold, often 0, the neuron fires. Step 5. Output. The output is binary, +1 if the neuron fires, and if it doesn't. Essentially, the perceptron is a simple binary classifier. It formalized the concept of using adjustable weights to learn a decision boundary, proving that a computational unit could adapt its response based on data. This breakthrough provided the very first viable building block for creating machine learning systems, even though its simplicity would eventually lead to major limitations. Despite the initial excitement and the development of early hardware, the limitations of the single perceptron soon became mathematically evident, leading to what is famously known as the decades-long AI winter. The promise was huge. The perceptron proved that machines could perform mathematical logic, and early devices were built to tackle image processing. Researchers believed the path to intelligent machines was simple and direct. The fall, however, was devastating. In 1969, Marvin Minsky and Seymour Papert published a landmark book demonstrating that a single perceptron was fundamentally limited. They proved it could only solve problems that were linearly separable. This means it could only classify data that could be successfully divided into categories using a single straight line. Any complex problem requiring a curved or disconnected decision boundary, such as the crucial XOR logic problem, was unsolvable for a single unit. This finding was widely interpreted as the end of neural network research, stalling funding and progress for years, treating the approach as a mathematical dead end. Fortunately, this stagnation wasn't permanent. The rebirth came decades later when researchers showed that Minsky and Papert's proof only applied to single perceptrons. By combining them into multi-layered structures and developing new techniques for training those stacked layers, these networks could easily surpass the linear constraints. This discovery validated the multi-layer approach and rekindled the entire field, setting the stage for modern deep learning. The modern artificial neuron, the true building block of deep learning, dramatically improves upon the 1957 perceptron by incorporating two critical mathematical upgrades. The first is Upgrade 1, the bias. In the original perceptron, if all inputs were 0, the output of the summation was always 0. The bias introduces a special, constant, learnable value that is added to the weighted sum. Think of it as a permanent intercept or offset. Mathematically, it shifts the entire function's activation profile left or right, up or down, allowing the neuron to adjust its decision boundary much more flexibly, regardless of the inputs. It is a vital tuning knob that we can adjust during training, giving the neuron increased computational power. The second upgrade, Upgrade 2, the activation function, replaces the perceptron's simple, binary threshold test. Instead of a hard cutoff, if sum 0, output +1, the activation function is a smooth or curved mathematical function that processes the final sum. The most crucial property this function introduces is nonlinearity. As we established, nonlinearity is the secret ingredient that prevents a deep network from collapsing into a single, equivalent linear unit. Without this activation function, stacking layers would be mathematically redundant. With it, each layer adds expressive, new computational power, enabling the network to learn incredibly complex patterns. To visualize and discuss neural networks effectively, we must first learn the conventional shorthand used in diagrams. On the left, we have the explicit diagram, which meticulously shows every element. The weighted inputs, W1, W2, W3 the red arrow indicating the addition of the bias, the summation \sigma$, and the activation function, the curved line. This diagram accurately shows what is mathematically occurring inside the neuron. However, when dealing with networks containing thousands or millions of connections, drawing every single weight line and the bias term becomes impossible. This is why we rely on the standard diagram on the right. In the standard view, the lines representing the weighted inputs flow directly into the neuron, but the individual weights, W1, W2, etc., and the bias term are entirely omitted from the drawing. They are implied. This is the key takeaway. In virtually all neural network diagrams, whenever you see a connection line, you must mentally register that there is a weight associated with it, and the neuron itself always includes a bias term. The weights and the bias are, collectively, the most important part of the neuron. Why? Because they are the only parameters the network can change or learn during training. Therefore, even though we simplify the visualization for clarity, remember that the adjustable weights and bias are always present and working behind the scenes. A single neuron, while powerful, is only the beginning. The real power of deep learning is unleashed when individual neurons are organized into layers that process data hierarchically. This organizational principle defines the feed-forward network. Information flows in only one direction, sequentially from input to output, never looping back. This structure is known mathematically as a directed acyclic graph DAG. The term acyclic confirms there are no circular feedback loops within the architecture, which prevents complexity and aids stability during training. The neurons are grouped into three distinct layer types. First, the input layer is simply where the raw data resides. It is not a processing layer. Next, we have the hidden layers. This is the computational engine of the network. Every complex feature extraction and intermediate calculation happens here. A deep network simply means one with multiple hidden layers. Finally, the output layer produces the final result, be it a score, a probability, or a regression value. Within this structure, the most common connection type is the fully connected layer. In a fully connected setup, every neuron in one layer receives an input from every single neuron in the previous layer. This dense connectivity allows the network to find intricate relationships and features within the data as it passes through the hierarchy. This slide brings us back to the critical issue that stalled AI development years ago: why nonlinearity matters. If we were to build a deep neural network but neglect to use a nonlinear activation function, the entire structure would immediately suffer network collapse. Here, we illustrate the concept mathematically. We have a two-layer system. Inputs A and B connect to hidden neurons C and D, which then feed into the final output E if the connections between these neurons only involve linear operations, addition and multiplication by weights. Then the entire system is redundant. Any combination of weighted sums across multiple layers can always be simplified and represented by a single layer, as shown on the right, A and B feeding directly into E. The new simplified weights, $WAE and WB, are simply complex combinations of all the previous weights, WAC, WBC, WC, etc. The core principle of linear algebra states that compounding linear functions yields only another linear function. Therefore, the depth provides no computational advantage. You might as well have used a single layer. This network collapse means the network would still be confined to solving only linearly separable problems, failing at the complex tasks required of modern AI. Nonlinearity is the necessary antidote to this collapse. The nonlinear activation function is the cornerstone of deep learning, providing the mathematical property that prevents network collapse and unlocks the ability to learn highly complex, nonlinear relationships. Let's contrast the two functions visually. The linear function on the left is a straight line. As discussed, a sequence of these can always be combined and simplified away. This is why a network built only on linear operations collapses. In contrast, the nonlinear function on the right contains a distinctive bend or kink. It is this mathematical non-smoothness that prevents the function from being algebraically combined and simplified across layers. Once this nonlinear operation is applied to the output of a neuron, the next layer cannot simply absorb the calculation of the previous layer. Instead, each new layer, empowered by the nonlinearity, is able to add genuine, new computational power, creating entirely new features and decision boundaries. This allows the network to model highly complex data, such as images where features don't separate nicely with a straight line. Without nonlinearity, we are stuck in the 1960s. With it, we unlock the capacity for sophisticated pattern recognition and deep learning. Now that we understand the necessity of nonlinearity, let's explore the specific functions used in practice, starting with the first group, the rectifiers. The dominant choice for hidden layers today is the ReLU or rectified linear unit. It is incredibly popular because it is both simple and computationally fast. Its function is straightforward. If the input is positive, the output equals the input. If the input is 0 or negative, the output is clamped to 0. The speed of ReLU significantly accelerates the training process compared to older, more complex functions. However, ReLU is not without its issues, most notably the dying ReLU problem. This occurs if a large, negative gradient pushes a neuron's weights so far that its weighted input is always negative. Once its input is consistently negative, its output is always 0, meaning the gradient flowing backward during training is also 0. This effectively kills the neuron, as it stops learning permanently. To address this, the leaky ReLU was developed. Leaky ReLU introduces a small, positive slope for negative inputs, typically a fraction like 0.01 times the input value. This small leak ensures that even if the neuron receives a negative input, a tiny, non-zero gradient can still flow backward, keeping the neuron alive and allowing it to eventually recover its learning capacity. Rectifiers remain the workhorse of modern deep networks. Moving on from the rectifiers, the second major family of activation functions is often referred to as the squashers, because they map the infinite range of possible input values into a finite, compressed output range. The first is the sigmoid, or logistic function. This function maps all inputs into an output between 0 and 1. This characteristic makes it extremely useful on the output neuron of a binary classifier, such as a model predicting yes-no or true-false, where the output can be directly interpreted as a probability. Historically, sigmoid was used in hidden layers, but it suffers from a significant drawback. For very large positive or very large negative inputs, the slope of the curve approaches zero, causing the gradient to vanish, slowing down training in deep networks. The second squasher is the tan, or hyperbolic tangent function. Tan is structurally similar to sigmoid, but it maps the input range into an output between -1 and 1. The key advantage of tan is that its output is zero-centered. Since the outputs of tan neurons average closer to zero, this often helps the optimization algorithms work more efficiently, which is why tan was historically preferred over sigmoid for hidden layers before ReLU became the default choice. While rectifiers now dominate hidden layers, both sigmoid and tan remain vital tools for configuring the network's final output based on the specific type of classification required. When a network is used for multi-class classification, such as distinguishing between class A, B, and C, the neurons in the final output layer typically produce raw, unnormalized values known as scores. These scores are raw numbers. They can be positive, negative, or large, and they do not represent probabilities. For a prediction to be useful, these scores must be converted into a meaningful probability distribution. This is the sole purpose of softmax. Softmax is a special mathematical operation that is applied to all output neurons of the classifier simultaneously. It is not an activation function applied per neuron, but rather a function applied to the entire output vector. The softmax function converts the raw scores into a valid probability distribution by exponentiating the scores and then normalizing them by the sum of all exponentiated scores. This ensures two crucial properties are met. First, every output value, prob A, prob B, prob C, will fall perfectly between 0 and 1, and second, all the resulting probabilities will sum exactly to 1. This makes the final decision easily interpretable, telling us exactly how likely the network believes each potential class is. The effect of the softmax operation is quite unique, as it serves two functions simultaneously. It preserves the rank of the scores while exaggerating the likelihood of the most probable class. Let's look at the example. Before softmax, we have the raw scores for classes A through F. Notice that class D has the highest raw score, followed by F, then see after softmax converts these into probabilities, look at the after probabilities graph. Class D still has the highest probability, towering near 0.95. This shows that softmax preserves the original order, ensuring the winning class remains the winning class. However, observe the other scores. While F and C were close runners-up in the raw scores, their probabilities have been dramatically reduced, or crushed, close to the zero line. This is the exaggeration effect. Because softmax uses an exponential function, even small differences in the raw scores are heavily amplified in the probability distribution. The class with the highest score gains near-total dominance over the total sum of 1. This characteristic is highly desirable in classification, as it provides a clear, high-confidence outcome, effectively making the network's prediction much more obvious by clearly defining the winner. We have now reached the culmination of our journey, the synthesis of the building blocks into a full thinking architecture. This diagram represents the foundational structure of a modern, deep, feed-forward neural network classifier. We started with the basic perceptron and upgraded it to the artificial neuron unit, incorporating a learnable bias and a nonlinear activation function. These units are then systematically arranged into fully connected layers, which define the complexity and depth of the network. The information flows sequentially and unidirectionally, moving from the input layer through multiple hidden layers to the output layer, forming the feed-forward DAG structure. Crucially, every neuron in the hidden layers is powered by a nonlinear activation function, e.g., ReLU. This is the mathematical key that prevents network collapse, allowing each layer to learn increasingly abstract and complex features. Finally, the raw scores from the last layer are processed by softmax, converting them into final, interpretable class probabilities that define the network's prediction. This hierarchical, nonlinear, feed-forward design is the standard blueprint underlying countless deep learning applications today, demonstrating how simple components, when organized correctly, can create a powerful, adaptive system capable of learning complex data representations. We conclude our exploration of the neural network structure by emphasizing one final critical point. The architecture is the blueprint, but the weights hold the knowledge. We have successfully defined the static, unchanging structure of the network, the number of layers, the type of activation functions, and the connections between neurons. However, a network with a perfect blueprint is meaningless if it hasn't been trained. If we were to run data through this newly built architecture with randomly initialized weights, the output would be random noise. The true, crucial difference between an arbitrary, untrained system and a powerful, predictive AI model lies entirely in the numerical values assigned to its weights and biases. The process we call training is the sophisticated, iterative journey of finding the optimal values for these parameters, which often number in the millions or billions. During training, the network adjusts these weights slightly with every batch of data it sees, gradually minimizing errors and encoding complex patterns from the real world into its internal parameters. When we talk about AI learning, we are really talking about the mathematical optimization of these weights. This transformation turns a random calculator into a tool that provides accurate, useful, and actionable results, and that is the topic for our next session: understanding how this powerful learning process actually takes place.